In this lecture, we're going to discuss the proof of unique factorization in the integers. So just to make sure we're all on the same page, let's recall what exactly we mean by unique factorization. So the theorem we want to prove is, let's do this for positive integers. So each, which we call the natural numbers. So each natural number n can be written uniquely as a product of primes. Okay, so what does that look like? We have n. We're going to be able to write that as some prime p1, possibly to some power, times p2 to some other power, etc., up to pk to some power. And, right, so everything is unique here. So all of the primes are uniquely determined by n, as are the exponents. I should say the one thing that's not technically unique is we could just reorder the factors. So let's say uniquely up to reordering. If we're allowed to just reorder the factors, then yeah, it's completely unique. So you can think of this almost as the chemical formula for the number n. These are the atoms and the number of times they occur. And so an example of this might be 60 is 2 squared times 3 times 5. That's the only way to write 60 as a product of primes, up to reordering these factors. So for example, I'll never be able to write 60 as 7 times something, or 3 squared times something. It'll be exactly 2 2's, 1 3, and 1 5. Okay, just for fun, here's another example. So 2023, the current year. That one is 7 times 17 squared. It's the only way to write 2023 as a product of primes. Okay, so you might think that this is a fairly obvious property of numbers, because primes are, after all, sort of the smallest building block. You can't break a prime up into two smaller numbers, essentially by definition of primes. What I'd like to do before even diving into the proof of this is I want to convince you that actually this is far from obvious. So yeah, let's just say so. This is surprising that we can do this. Not that we can factor it into primes, but the fact that there's only one way to write it as a product of primes. I want to show you that this is actually really surprising. And the way I'm going to do that is I want to show you that this can actually fail in other number systems. So this can fail. This can fail in other number systems. Okay. So let's sort of invent another number system. Let's look at, so we'll include a 1, so that's sort of the multiplicative unit. But let's look at, I'll call this 4z plus 1. So all numbers that are 1 more than a multiple of 4. Yeah, this all positive. Let's just look at the positive ones for now. All positive integers of the form 4k plus 1. K is an integer. Okay, so what am I talking about? 1, 5, 9, 13, 17, 21, 25, 29. Let's go a bit further. So 33, 37, 41, 45, 49. Okay, we'll stop there. Okay. First thing I want to do with this new number system is define what I mean by prime. So a number is prime in this number system. So a number is prime. I'll put it in quotes because it's not going to mean the exact same thing as for the integers, because we don't have all the integers here. So a number is prime if, well, we'll try to use the same definition. So if it cannot be written in the form, so we'll call that number p is prime. So it cannot be written in the form p equals a times b, except for a equals 1 or b equals 1. So these are, we're going to allow 1 to divide our number. But yeah, if we cannot decompose it as two numbers like this, I want to emphasize, however, so this is, so except a equals 1, b equals 1, where a and b both belong to our number system, right? We're going to pretend these are all the numbers. So a and b also have to belong to this 4z plus 1. Okay, so what I mean, so, well, 5 is clearly prime. 5 we can't even write in this form, even if we go outside of our number system. So all the numbers that are prime in z are also going to be prime in this number system, so etc. 1 is not going to be prime. 9 is not prime in z, but it is prime in 4z plus 1. And that's because I can't write 9 as a product of smaller elements in this number system, right? My only smaller number is 5, and I can't write it as 5 times 5 or anything like that. It's 3 times 3, but 3 is not in my universe here. Okay, let's keep going. So similarly, 21, I mean, the only way to write that without a 1 is 3 times 7, but neither of those live in 4z plus 1, so this is also prime. So I have more primes in this number system. Actually, well, I shouldn't say that because I'm sort of also losing out in some primes, like 3, 7. But yeah, it's sort of easier for numbers in this number system to be prime. Is 25 a prime? No, actually, right? Because it's 5 times 5, and 5 lives in our number system. But 29 is 33 a prime? I believe so. So it would be 3 times 11. Neither of those are here. 37 and 41 are certainly primes. Those are prime in z. 45 is not a prime, right? It's 5 times 9. Those are both living in our number system here. So 45 is not prime. 49 is a prime, though. It's 7 times 7, but 7 is not in our number system. And that's the only way to write 49. So you get the idea. So these are primes. And we would like to maybe say that any number in this number system can be written uniquely as a product of these primes. Primes in quotes. Well, that seems fairly reasonable. So for example, if we had 65, that has a factorization here. It's 5 times 13. And that's the only way to write 65. You might think, yeah, this looks like unique factorization probably holds here as well. It turns out that it doesn't. And, actually, but it's rather difficult to construct an example, but I think we actually can do so with the numbers here. Yeah, so 9, I'm gonna go outside of my number system for a second just to construct an example. So 9 is 3 times 3, 49 is 7 times 7, and 21 is 3 times 7. So here's what I'm going to do. I'm going to look at the number 9 times 49. Okay, which is, what is that? It's 441, I think. That's 9 times 49. See, outside of my number system, this looks like 3 times 3 times 7 times 7. But see, I can also get the same number by doing 21 squared. This is also the same as 21 times 21. Both of them will have 3 3s and 2 3s and 2 7s. But what you notice here is that in my new number system, these are all primes. So I've actually written 441 as a product of primes in 2 different ways. So unique factorization fails here. It fails for this number system 4z plus 1. Okay. You can kind of see what's going on, though. This is sort of smaller than my integers, and if I go to the integers, all the integers, then I can actually further decompose these, and I see that this is actually just the same factorization on both sides. But I had to go to a larger number system, the full integers. So that's a bit subtle, but you might be saying, well, okay, it's just because we didn't take all the integers, we took something smaller. Well, that's not the end of the story. So what if I go to something bigger than the integers? That includes all the integers and some more things. So for example, what if I go to, this is a number system we saw last time, the Gaussian integers. So this is all integers of the form a plus bi, where a and b are just normal integers. I is the square root of -1. Okay, and we defined what we meant by Gaussian primes in the last lecture, and we can ask, does unique factorization hold here? It turns out it does. So unique factorization works. Factorization works here. I won't go into the proof. It actually is going to be pretty similar to what we're going to do today, but a little bit more involved. So I think, okay, well, this is great. So if we go to something larger than the integers, then we're fine. But this next example might blow your mind a bit. I know it did for me. Let's go to this one. So z adjoin square root of -5. Instead of square root of -1, I'm going to put it as square root of -5. So just all numbers of the form a plus b times the square root of -5. So these are also complex numbers, a subset of the complex numbers. And it turns out that I can write, let's take the number 6. Okay, so 6 is certainly not a prime. So at the very least we can factor it as 2 times 3 in these integers here. I don't know if there's a standard name for these or not, but so we can write it as 2 times 3. We might be worried that maybe 2 and 3 are not prime in this number system. It turns out they still are. But we can also write 6 in this way. 1 plus a square root of -5 times 1 minus a square root of -5. These are perfectly good elements of this larger number system. If you multiply this out, you get 1 squared, and then these two middle terms are going to cancel, and you're going to get a minus -5. So 1 plus 5 is 6. And it turns out that all of these are prime. All of these elements here, these are all prime. And so unique factorization actually fails here. But it fails here. It fails here, which is very strange. This almost reminds me of this example up here, where we're in a smaller number system, and we could further break this up into 3 times 3 and a 7 times 7. It turned out that someone named Kummer had the idea to do this. Kummer, in the sort of mid-1800s, to sort of write this 2 as maybe P1, P2, and then this 3 is P3, P4, and try to figure out what P1 and P2 had to be in order to such that P1, P3 equals this thing, and P2, P4 equals this one, or something like that. So basically the same idea here. But yeah, essentially this problem led to the concept, and Kummer called these the ideal numbers. So if you want to look something up, the ideal numbers. And this led to what's known as an ideal in ring theory, which sort of formed the basis for all of 20th century algebra and algebraic geometry, and number theory as well. So yeah, basically there's something really mysterious going on here, and attempts to sort of unravel what's happening here led to a lot of interesting mathematics, even if this one particular problem itself maybe doesn't seem like it has any applications. Okay, so well, let's go ahead and prove unique factorization for the integers. Factorization for z. But I hope now that you can kind of see that the argument's probably going to be pretty tricky and subtle, because somehow it should work to prove unique factorization here, but not here, and not here. So there's something that's going to be very subtle about the argument. So that's just to kind of prepare you for that. Yeah, we want to prove this statement up here. So every natural number can be written uniquely as a product of primes. All right, so there are two parts to this statement. The first part is we want to know that factorization exists. So there's the existence part, the existence of a factorization. Into primes. And not just a factorization. We know we can factor numbers, but can we factor all the way down to primes? That part is fairly obvious because, in fact, I think we already did it in our induction lecture. But if you're starting with a number, you can certainly break it down into smaller numbers, product of two smaller numbers. If you can't, and the number's prime to start with, and we already have a factorization. If you can, then we get some smaller numbers, and then if we know it's true for the smaller numbers, it's true for the larger numbers. So essentially, that's just induction. So this part, this just follows from induction. It's the second part that's trickier. So the second part, we have to prove that there's only one factorization. So the uniqueness of a factorization. Maybe I'll just warn you here that this is actually rather tricky. This is the tricky part. We're going to do it today. And you can see why it has to be hard again just by thinking about these examples. Like there's something very subtle going on here. Okay, well, nonetheless, let's try to prove this. So suppose, how do we prove uniqueness? What I would do is I would suppose we have two different factorizations. Suppose we have two different, or maybe not even. Let's just suppose we have two factorizations, and we want to prove they're the same. So we don't even have to assume they're different. Let's just say we have two factorizations for some number n. So let's write out what those are. First one, we'll use p1 to the e1, p2 to the e2 times ... pk to the ek. There's my first factorization. Let's suppose I have a different one. q1. I'll call it something different. At the end of the day, I'm going to try to prove that all the q's and the p's are the same. And it's actually the same factorization. All the exponents are the same as well. Let's suppose we have something different. I'll even call these exponents something different. So like f1, q2, f2, etc. qk to the fk. We can assume like all the p's are distinct too. So the pi are distinct. And same with the qi. So I'm not writing 2 to the 3 and then 2 to the 5 over here. It's just I combine them to be 2 to the 8. Okay. Well, let's think about this. So we want to show that actually these just look the same. So we want to show that the idea is we're going to take one of these pi's, p1 to the e1, let's say. And we want to show, it's going to be the idea, that this appears in the second factorization. That exact prime appears with the exact exponent actually appears over here. How are we going to do that? It's actually rather tricky. And let's go to another page. This is going to rely on the following statement. And so because I'm about to write what's essentially the key idea of the proof, and this idea is actually interesting in its own right too. So what I'm going to do is I'm going to call this a lemma. A lemma is a really important step in a proof that you sort of want to draw attention to. This is actually a key idea that's being used in a proof. And this is actually called Euclid's lemma. So it's also found by Euclid. Euclid's lemma is a statement about primes. So the statement is, if a prime divides a product. Let's just do this for two numbers. So let's call it A, B. A times B, product of two numbers, two integers. Then the conclusion is that P has to divide A itself, or P has to divide B. It's not an either or, so it could divide both of them, but it has to fully divide one of these. Okay, so you have to be careful because this actually is not true if P is not prime. Let's just look at a couple examples first. So, for example, 4 divides the product 2 times 6. 4 divides 12. But, so just to be careful, 4 divides this, but 4 does not divide either part of that product, right? So 4 does not divide. That's a symbol for not divide. And also 4 does not divide the 6. If we chose a prime that divides 12 instead, let's say 3 divides 12, and I'll write 12 as this product, it turns out that 3 is going to fully divide the 6. 3 fully divides the 6, which is what this is saying. It's going to fully divide one of these two factors. Great. So that's Euclid's lemma. Let's prove Euclid's lemma. So a proof. Let's take any arbitrary product, and we'll suppose that P divides it. That's what we're assuming here. We want to show now that it has to divide one of these. So if it divides A, we're done. So let's suppose it divides this product, and P does not divide the first one. Well, what do we want to prove? We want to prove that it has to divide the second one, right? So we want to prove that. It's just right up here. It's good to keep track of what we want to show. So we want to show now P has to divide B. Okay. Well, you might say, okay, well, you just write out the prime factorization of this, and if it doesn't divide A, then P doesn't appear in the prime factorization of A, so it appears in the prime factorization of B. But that's circular logic because we're using this. We're using the existence of unique factorization in the first place, so we can't do that. So this is actually, when you think about it, it's rather tricky. We're going to use this as a step to prove the unique factorization after we prove this Euclid's lemma. All right, so we want to show this. Well, what do we know? If P does not divide A, then I mean, one thing we definitely know is that GCD of P and A is 1. P and A are coprime. Right? Because P only has two factors, 1 in itself, and we know that P does not divide A, so these can't have any factors in common. All right, now comes the really cool part. So we're going to actually use the Euclidean algorithm. So by the Euclidean algorithm, by what we did before, by the Euclidean algorithm, you'll remember I said this algorithm holds many more secrets than just being able to find GCD. This is sort of the main one. It can be used to prove the fundamental theorem of number theory. So by the Euclidean algorithm, well, we can do a lot of things, but in particular, you'll remember we can write the GCD as a linear combination of P and A. That's what we did by using the Euclidean algorithm symbolically. We were able to get 1 as a linear combination of P and A. So we can write 1 as P times some x plus A times some y. I mean, one of these x and y will have to be negative in order to make this happen, but that's okay. So x and y are in Z. Okay. Okay, great. Well, where are we going with this? We want to show P divides B, so we need to make B appear here somehow. The way I'm going to do that is I'm going to multiply this equation. Multiply this by B. Both sides. So B equals PBX. So x and y are just some integers. I don't really care what they are. ABY. Okay, well, you might say this looks kind of strange. I have a B everywhere, so why am I doing this? Well, here's what we can now conclude. So this term here, P certainly divides this term. So P divides this. Why? Because there's a P sitting right there. But P also divides this term. P divides this too. Why is that? Because we're assuming P divides this product A and B, and I made this product AB appear. At the same time, I made a B appear over here. It's a really nice little argument. So, and so now we conclude, actually, P divides both of these. It has to divide the sum, which is B, right? So that these two things imply that P divides B, which is what we want to prove. And we're done. So that's the proof of Euclid's lemma. So I'll separate this. This is also an important lemma in its own right. It can be used for other things too. But this is actually the sort of key insight that we're going to use to prove that any two factorizations into primes actually have to be the same one. So let's actually go back to that. We'll go ahead and write our factorizations out again. So we've got there's Euclid's lemma. We have n. It's going to equal P1 E1, P2 E2, etc. to Pk e to the k. Let's say we can also write it as Q1 F1, Q2 F2 to Q. You know, I shouldn't call this k actually. I should call it something different. Maybe there's a different number of factors here. Say L. Okay, what do we do now? Let's take a prime over here. Let's say to P1. So take a prime on the left side. Let's say P1. And we see actually that P1 has to divide, well, n, obviously, right? N has it as a factor. But n we can also write this way. So it has to divide this whole thing right here. Well, does that mean that P1 has to divide one of these terms specifically, or even one of the Q1s specifically? It turns out that yes, it does actually. And the reason is this Euclid's lemma. So a prime, if a prime divides a product, it doesn't matter that the product has primes. It's just we start with a prime. I should have called that prime P. Right? If a prime P divides a product, then either it divides one part of the product or the other. I can take this product and split it up however I want, right? So I can, for example, split off this first prime, can write it as this times the rest of it. By Euclid's lemma, p has to divide one of those parts. Okay, we've reduced it to a smaller problem. Let's say p has to divide this part. You keep doing it. You keep splitting off a q. And so we conclude that, so by Euclid's lemma, let's say by repeated application of Euclid's lemma, we conclude that actually p has to divide, p1 has to divide one of the qi's even. You might say, well, okay, we've only proven it divides qi to the f I for one of these terms. Well, wait a second, that's a product too, right? This is qi to the 1 times qi to the fi minus 1. And now by Euclid's lemma, either if p divides this, it has to divide either this part or this part. If it divides that part, then we're done. If it divides this part, we have a smaller problem, right? Our exponent has gone down by 1. So essentially we're using induction again here. But just by repeatedly applying this, we're going to be able to conclude that p1 is going to divide one of these q's over here. But wait a second, q is prime, right? So that qi is prime, whichever one it is. So the only way a prime can divide another prime is if they're the same prime for some qi. Okay. Now I think you can probably see the idea of the rest of the proofs. So we've essentially proven that one of these primes is also going to be one of these primes over here. Okay. Right, and the exponents will have to match too, because so I'll just say furthermore the exponents must match. So p1 to the e1 has to actually equal qi to its exponent over there. The exponents have to be the same. Why is that? Well, if they didn't match, you'd have a leftover p1 on one of the sides. It might be this side, it might be that side. But you can just continue the process, right? If you end up with a p1 on this side, that's going to have to divide one of these terms that are left here, which I mean, we're assuming they're all distinct, so that's just not possible actually. So yeah, however you want to argue it, one of these whole factors here actually. So for example, this one here just has to exactly match up one of these factors here. I said Q2F2, but it could have been a different one. Great, and then you can just continue this for all of the primes here. You're eventually going to get down to 1 equals 1. I mean, you'll get a 1 on this side, but you have equal factorizations, right? Because they both equal 9. So we eventually get a 1 equals 1 just by repeatedly dividing. Just keep dividing both sides by whatever prime on this side we have, and then repeat the argument. We have a finite number of terms. Eventually we're going to do it with all of the terms, and we're going to get a 1 on this side, and then we'll have to get a 1 on that side too, because they both are equal. All right. So what do we conclude? So if we get the same thing on both sides, we were dividing by equal things, so the factorizations, so the original factorizations had to be the same. Had to be the same. Not just equal to the same number, but literally every term in here has to correspond to some term here. All right, so that's the proof of unique factorization. But that was rather tricky. I hope you'll agree. We used some induction here. We used a lot of things, right? So we used this Euclid's lemma, which itself was sort of resting on this fact that we can write 1 as a linear combination of two coprime numbers, which is using the Euclidean algorithm. And this is, even the Euclidean algorithm is sort of resting on a lot of things. So it's resting on the fact that we can do this division with remainder, right? Where we can write a equals qb plus r. We can repeatedly subtract off b from a, and then be left with something that's actually smaller than b. We can just continue subtracting off. And these are all things, I mean, you can come back to these examples and try to imagine like what's going wrong in maybe this example and this example. Well, actually multiple things going wrong, but yeah, essentially it's hard to define a Euclidean algorithm here because it's hard to actually show that you can keep doing this and getting something smaller each time to work with. It might never terminate. Okay, well, that's the proof of unique factorization. Let's now try to apply this. So what do we know? We know that any integer, from now on, whenever we have an integer, we're going to think of it as a product of primes. So E1, P2, E2, ... multiply them all together, pk to the ek. We can write our integer as a product of primes with all the pi are distinct. And this is the only way to write n as a product of primes. So this is the prime factorization. This is the prime factorization of n. So one and only one way to do it. Okay. This is great because we can actually take a look at this this factorization here and deduce a lot of things about our number n. So for example here, so yeah, maybe this section will be applications. First application. Given a prime factorization, so given the prime factorization, I can say the prime factorization. We can easily find all the divisors of a number. Without the prime factorization, it's hard to find divisors. It takes a long time. It's very time consuming, as you've probably experienced. But we can find all the divisors of a number if we're given the prime factorization. Let's do 60 as an example. So 60 is 2 squared times 3 times 5. Well, let's say I have a divisor of 60. It's going to have a prime factorization. It has to be a subset of this prime factorization. It can't have primes coming from elsewhere. It has to involve the primes here, right? Because when you multiply that by something else, you get 60. There's only one way to write 60 as a factorization into primes. It's this way right here. So all the divisors are just sort of subsets of this one. So I can sort of write them all down. So I can either have I'm going to try to make a divisor from scratch. So I can have either 0, 1, or 2 2's, right? I can have 0 or 1 3. Right? I don't have to take the 3 to the 1. I can just ignore the 3. This one I can take 2 to 0, 2 to 1, or 2 to the 2. And I can take the 5 or not take the 5. Right? So I can have 0 or 1, 5. So let's say I pick I don't know. Let's pick 1, 2. We'll pick 0, 3's, and we'll pick 1, 5. What divisor does that get us? That gets us 2 times 5, which is a divisor of 60. We can get them all just by taking all the combinations here, essentially. And this actually leads immediately to something very useful, which is we can essentially count the number of divisors of 60 just almost immediately here. Because so we have 3 choices here, and we have 2 choices here, and we have 2 choices here. So the number of divisors of 60 is so you have 3 choices for the 2. There's like choices. That's how many choices for the power of the 2. And I have 2 choices for the power of 3, and I have 2 choices for the power of 5. Right? Because I can choose a 0. And this gets me 12. So it's actually saying 60 has 12 divisors. And you can try to list them all. And you'll find out that there are indeed 12. And notice if I take the 0 for all of them, I get 1. Right, so I have none of each of these. So I'm just starting with the empty product, which is 1. And if I take the maximum, I'm going to get 60. So this is actually the number of all divisors, not the proper ones. It's just all divisors, including 60 itself. So there's also a really neat observation here that, where are these numbers 3, 2, and 2 coming from? They're coming from the number of possibilities we had for each of these primes. So we're essentially choosing what exponent we want each prime to have when we're building up a divisor. And so we can actually write down very generally. So the number of divisors of any positive integer n, so let's write n as its prime factorization, we can just write out a formula for it. Because we're going to have some p1 in our divisor. Maybe we don't have a p1, but that will correspond to choosing a 0 here for the exponent. So we can choose 0, 1, 2, all the way up to this power. So that's going to be e1 plus 1 choices, right? Because we're allowed to choose 0. Same with p2. We have up to e2 plus 1 choices, because we're also allowed to choose 0. 0, 1, 2, all the way up to this number e2. And up to ek plus 1. So this is just a formula for a number of divisors of a number. If you have its prime factorization, we're assuming we have this already, or we can get it, then you just add 1 to all the exponents, multiply them together. That's the number of divisors. Okay. So let's do this for 2023. I'm going to tell you that, I told you before, but it's 7 times 17 squared. So can you see how many divisors 2023 is going to have? Well, it has, I look at the exponents in my prime factorization. I don't even care about the primes, whether it's 17 or 41 or whatever. It's the exponents that matter for number of divisors. So it's going to have, my e1 is 1, so it's going to have 1 plus 1 times 2 plus 1. Which is 2 times 3, which is 6. So 2023 has exactly 6 divisors. And you can write out what they all are. So you either take one of these, so or 1, or we can take a 17 or 17 squared, or we can take a 7 in our divisor. And we can have a 7, we can have a 7 times a 17, or we can have a 7 times a 17 squared. Or this one is 2023 itself. Okay, let's look at one more nice application of this. So application 2, we have also formulas for GCD and LCM. I'm not sure if I talked about LCM yet. So what is LCM? LCM means least common multiple, which is exactly, that's basically the definition there, so I don't really need to say any more than that. But yeah, what do I mean? So I have the LCM of 2 numbers. And so what I mean is I want to take all multiples of each of the numbers and look for the ones in common, right? So the multiples are going to coincide sometimes. and I want to take the smallest one of them, the least common multiple. Let's do an example. Let's do GCD and a LCM. You might say we don't need a formula for GCD because we can do it so fast with Euclidean algorithm, and you're right, actually. But if we happen to have the prime factorization, there's actually going to be an even quicker way to write it down. So GCD of, let's just pick two numbers, 6 and 10. The GCD is 2. 2 is the greatest common divisor of 6 and 10. Whereas the LCM, we look at multiples of both of these. So 6, 12, 18, 24, 30, etc. 30 is probably as high as I need to go because the multiples of 10, 10, 20, 30. So LCM is 30. Okay, well, how do you find the GCD of two numbers? Let's use this example even. So 6 is 2 times 3. I'm looking at the prime factorizations now. Let's say we're able to factorize our numbers. The GCD is sort of what we have in common here in the prime factorization. So we see the 2. We can take these 2's to be in common. And these parts are different, right? The 3 and the 5. So for the GCD, we want to take sort of the maximum of what's common between both our factorizations. So that would be the 2. I think let's actually choose a slightly more complicated example just to see exactly what we're doing here. So 60 is 2 squared times 3 times 5. Let's also choose another number. Let's do 45. So 45 is prime factorization as 3 squared times 5. And the GCD, well, I need a common divisor of both of these. And so certainly that can't include any 2's because 45 doesn't have any 2's. So I don't want any 2's. I do want the 5. Okay, but I also want the 3, right? Because there's a 3 in common, but I only want one 3, not both of them, right? So if I take both of them, then that won't be a divisor of 60 anymore. 60 only has one 3. So I only want one 3. So I'm essentially taking, for each divisor, for example, 2, 3, 5, I'm taking the smallest exponent, so sort of the minimum exponent. So this is 3 to the 1, 3 to the 2. I'm taking, so what am I really taking here? So I'm taking 3 to the sort of minimum of the 2 exponents. Because otherwise it won't be a divisor of both numbers. Okay. That works here too with the 5's, right? I'm taking, they both appear to be exponent 1, and I'm taking that one. With the 2's, you can imagine I sort of have a phantom 2 over here. That's just to the exponent 0. And I'm taking a 2 to the 0 because I don't have any 2's here. So in general, what this is so if I have, well, let's write out two different numbers. So let's say A is, you know what I'm going to do here? I'm going to use actually the same P for both of them. So I won't do P's and Q's. I'll just do the same P's for both of them. You might say, well, wait a second. They're not going to have the same prime factors in both of them. Well, that's fine. I'm just allowing the exponents to be 0. So B is P1. These could be different exponents. So F1, P2 to the F2. So it's the same primes. I'm just allowing, so I can allow any of the EI's to be 0. I probably should have said that at the beginning when we stated unique factorization. It's uniquely a product of primes where all the EI's are positive. So otherwise you could just do kind of ridiculous things like put another prime in here to a 0 exponent. And that would be a different factorization. Okay, so what is the GCD of A and B? Well, I go through all of the primes and I take the minimum exponent I'm allowed. Right? So Because if I take anything larger, then it won't be a divisor of one of them. But I do want the greatest common divisor. So I'm going to take as much as I can. So I'm going to do P1 to the min of E1 and F1. Okay. Maybe one of them is 0. That's fine. That means I shouldn't take any of that prime. P2 to the min E2 F2, etc. All the way up to the last prime here. Min EK FK. Okay, so that's the formula for the GCD. What about the LCM? Well, for the LCM, it's actually a very similar process. So I want a multiple now of both these numbers that sort of includes the entire factorization of both of them. So the best way to do that, so let's say I want the LCM of 60 and 45. I'm going to take, so I have 2 to 0 here, 2 to 2 here, 2 to 0 there. I want to take the 2 to the 2. So it's going to be 2 to the 2 times, right, because I want a multiple of this, so it needs to have at least 2 2's in it. And I need a multiple of both of these, so it needs to have at least 2 3's in it because of this one. So now I'm taking the maximum of the exponents. And now I need the 5 also, because I want to be a multiple of both of these. Notice I didn't do 1 plus 2 here, right? I only need two 3's, and that's already guaranteed to be a multiple of that one too. So these 2's are sort of the maximum. Yeah, let's just write out the formula. I think you can maybe see where we're going. So P1 to the max of the E1 F1, P2 to the max E2 F2. PK to the max of EK FK. So that's how you find LCM. And I just want to note one interesting thing before I end the lecture, which is what happens when we do the GCD of A and B times the LCM of A and B. Let's look at our formulas. So we'll go one prime at a time, right? So we can write this GCD as P1 to some power. The LCM is also going to involve this P1 to some power. So I'm going to have sort of a P1 to the min times a P1 to the max of these two. Well, one of them is a min and one of them is a max, right? So say E1 is the min, F1 is the max. I'm going to get P1 to the E1 times P1 to the F1 and multiplying them together. So I'm going to get P1 to the E1 plus F1 by the properties of exponents. And similarly, I'm going to get P1 to the min of E2 F2 plus the max of E2 F2. One of them is a min, one of them is a max, so I'm going to get both of them. If they're both the same, then this still works. And you keep going until we get Pk to the Ek plus Fk. What is this? Well, this looks like just these two factorizations sort of smashed together, right? Multiplied together. So the factorization for A and the factorization of B sort of multiplied together. So this is the same as, I sort of again use the exponent properties. E2 all the way up to Pk e to the k times, again I've got some P1 to the F1, P2 to the F2, etc. all the way up to Pk to the Fk. But this thing right here is none other than A, and this is none other than B. And we actually just showed something really interesting. So the GCD of two numbers times the LCM, the greatest common divisor, the largest divisor in common, times the smallest multiple that's in common, is equal to the product of the two numbers. Okay. Does that work here? So the GCD of 6 and 10 is 2. The LCM of 6 and 10 is 30. 2 times 30 is 60. That's exactly the product of 6 and 10. This works more generally too. If your numbers are negative, you have to be a little careful about how you define these. Maybe you have to put absolute value bars on here. Yeah, so one actual really important use of this formula, and then I promise I'll stop after this. So an important use of this formula. We talked about how GCD can be computed really quickly with the Euclidean algorithm. Well, if you can compute the GCD, you can compute the LCM. Because this product equals AB. So if I do A times B, multiply my two numbers together, then divide by the GCD. Well, this GCD I can compute very quickly. Certainly this product I can compute quickly. This division I can compute quickly. So that means I can compute this quickly. So I can compute this quickly. I mean quickly in sort of technical way in terms of computing, but yeah, there's a very efficient way of computing the GCD, which is the Euclidean algorithm. You can do 100-digit numbers very quickly with the computer, even. And so this fact here is actually rather important because it gives us an algorithm for computing the LCM. All we do is use the Euclidean algorithm for GCD, and then use this product formula here. Okay, thanks for watching.